gives us the opportunity for distinguished scientists to come and visit us and explain some of the work that they've been doing. The National Groundwater Association is located here in Columbus, and we're fortunate that they have brought their videotaping crew here, or hired a videotaping crew, and this is part of another program that they have to make the videotapes of these lectures available. And one of my students, Dave, up there, has been giving out information that explains the history of the Henry Darcy groundwater series and talks about some of the previous lectures and talks about the availability of videos. So if you like what you see here in gym, you can order some of these videos. They're relatively inexpensive and very good. And that's one of our claims to fame here, because we're always convenient for videotaping, so we're always glad to see the Darcy lecturer. Also provided there is information about the Groundwater Scientists and Engineers newsletter. Many of you, I'm sure, are NGWA members and get this as a matter of course. But if you're interested in finding out about the programs and finding out what's going on and so on, there's material there as well. Also located up there is a brief abstract of Jim's talk with a few pertinent references. And also, just to give a plug, there will be a conference at the beginning of May operated here in Columbus on tills as well. So it's a topic well worth interest. Well, without further ado, I'd like to introduce this year's Henry Darcy lecturer, Jim Hendry. Jim Hendry is the Chemical professor at the University of Saskatchewan in Saskatoon. Jim has a degree from the University of Waterloo that he received in 1984, and his interest is in the geochemistry of reactions in waste piles, and also in the development of understanding of behavior of Aquitards systems. So Jim's talk today is entitled Transport and Geochemical Controls on Solutes in Clay Aquitards. And this represents work he's been doing over the last several years and recently published in Water Resources Research. So without further ado, I'd like to introduce my friend and colleague, Jim Hendry.
Thanks, Frank. Thank you very much for that introduction, Frank. And it's nice to be back at Ohio State. Nice football stadium you're building. What I'd like to do over the next 50 minutes is talk about some of the research that I, my graduate students, colleagues, collaborators, research assistants, and postdocs have been working on for 6 years. I consider this a work in progress. It's probably going to take another 6 years before we get to the point where we thoroughly understand what's happening in the systems we've been studying. And these systems consist of aquitards, primarily clay aquitards, clay-rich aquitards. As Frank said, the title of this presentation is The Transport and Geochemical Controls on Solutes in a Clay-Rich Aquitard System in southern Saskatchewan, Canada. And this clay aquitard material, I won't say it probably again, but you can think about it. This clay till aquitard system we're considering as being non-fractured. Now, aquitards are important. I think they're important. Let me take a moment and try and convince you why I think they're important, and hopefully you'll believe they're important. First of all, they're arguably the most common geologic or hydrogeologic unit in the subsurface. They're also the material of choice if one wanted to dispose of waste. They also have an impact on the chemistry of underlying or overlying aquifer systems. That being, they've acted as a source of salts and soluble organic acids for these aquifer systems. They also have an effect on the hydraulics of aquifers. They do impact aquifer testing. So that's the importance of the aquifers. That's why I think aquitards are important, What do we know about these aquitards? Well, we know very little. We know very, very little about the hydraulics of the system. The hydrogeology of aquitard systems is poorly studied. As far as the geochemistry, the reactive transport of solutes in aquitard systems, there's no published information. So we're babes in the woods when it comes to the geochemistry of these systems. The little bit of work that has been done on the hydraulics or the advective transport in these Aquitards systems has been done on conservative tracers. These tracers indicate that solute transport in Aquitards is dominated by diffusive processes. Not advective processes, but diffusive processes. I hope by the end of this presentation we'll all be in agreement with that solute transport in Aquitards, these Aquitards in particular, is dominated by diffusive processes. So there's been very little bit of work done on Aquitards. Why is that the case? Well, I've listed what I think the main reasons for the lack of work in Aquitards. The first point is they take a long time frame to study. We're talking about trying to obtain water samples from materials that yield water very slowly. Some of the instrumentation I'll be talking about in the study area we'll be discussing yield in the order of 500 milliliters of water every year or year and a half. Extremely slow yields. That's the main problem, long time frames, and as most of us can appreciate, long time frames are not conducive to obtaining funding from funding agencies. They would rather see something over a 3 to 4 year period rather than something over a 10 to a 15 year period. The second point are technical difficulties. There's a number of technical difficulties when trying to study the advective or transport processes in these Aquitard materials. For example, we're interested in chemistry. We're interested in chemistry, the pore waters in these materials. Chemistry is in the order of parts per billion, sometimes down to parts per trillion. Our main concern is the chemistry we're obtaining from these water samples that sit in these piezometers for long periods of time, take a long period to collect in the piezometers, is this water representative of formation water or has it undergone some sort of chemical reaction? And what we are actually studying is a remnant of what's happened in the piezometer itself. The third point relates to the first two. It's costly. It's costly to instrument, it's costly to monitor, and it's costly in manpower because you need a lot of manpower over a long period of time. The last point is it's multidisciplinary. I've been involved in multidisciplinary studies for a number of years. To me, this is the most multidisciplinary study I have been involved with. We need geochemistry expertise, isotopic geochemistry expertise, hydrogeology, and microbiology. All four of these have to be working in concert, have to be advancing at the same pace, or else we just can't get our publications out. Everybody has to be working on the same page, and that's proved very effective in this study. Now's a good place, I think, to introduce the acknowledgments. When I say we, when I say I mean these are the people that have collaborated on the aspects of this Aquitard work that I'll present. There's a number of other areas that we're working on with respect to Aquitards. We won't talk about those. They're not represented here. So these are the people that some of whom should be standing up here as well. As far as funding, I said it's a long time frame, takes a considerable amount of money. These are the funding agencies for this work that I'll be presenting for the next 45 minutes. With that said, now, how are we going to approach this presentation? If I was talking to you about reactive solute transport in an aquifer, I'd start off by describing the geology, then I'd go into the solute transport, and then I'd go onto geochemical controls. Since we're talking about an Aquitard system that I'm going to spend probably the next 6 years of my life on, as well as the previous 6 years of my life, site selection was critical. To me, site selection was the most important aspect of this whole study. We were going to study a site for 12 years, 15 years. It had to be the right site to study. So I'd like to introduce some information on site selection criteria for this Aquitard research work that we're doing. The other point I'd like to introduce is sampling and instrumentation. I would like to try and take a few minutes and convince you that the samples that we are collecting, have collected from these piezometers are representative of formation material. Because I had to convince myself initially. So we had to design an instrumentation program that we thought would work. And I'll present information on that, sampling and instrumentation. The first thing I'd like to talk to you about is the criteria for selecting this detailed study site. The limited bit of work that's been done on Aquitard research, mostly the hydraulics, mostly the advective, has dealt with a thin Aquitard, typically less than 30 meters, underlain by an aquifer. Now, we're studying long-term solute transport in the order of thousands to tens of thousands of years. We know that aquifer systems are fairly dynamic. They're dynamic hydraulically, they're dynamic chemically. So what this dynamic nature in this aquifer does is it imparts signatures that we think would be very difficult to interpret at the bottom part of the Aquitard. and we were interested in the bottom part of the aquitard. So the way we got around that problem was we put another aquitard into the system. Deal with an aquitard, then underlain by an aquitard, then we could have whatever we wanted under there. In this site we're looking at, we have an aquifer underneath it. So we're looking at a two-layer aquitard system, or two-aquitard system. The other point we wanted was we did some simulations, some theoretical simulations based on transport, what thickness of these aquitard materials, what thickness should these aquitards be? And the minimum thickness we required was 60 meters. 60 meters for the upper aquitard, 60 meters for the lower aquitard. So that was sort of a criteria we set for ourselves. The third point, or the second point identified in this bullet, the second point is we wanted an unconformity between the two aquitards. I wanted two aquitards that were hydrogeochemically different as well as hydrogeologically different. Because I'm interested in studying the processes, or the transport processes, across the interfaces between the two aquitards. The fourth and fifth point, you can almost look at them together. We wanted aquitards that did not have extensive sand streaks or sand layers in them, because we wanted to deal with the world in a one-dimensional system. By having sand streaks and sand layers, we'd have fluxes in and out of the system that we couldn't control. So we're looking for aquitards that were aquitards. They did not have sand layers or sand streaks in them. The other point is we wanted these aquitards to be laterally extensive. Again, by being laterally extensive, we can convince ourselves that we're dealing with a one-dimensional system, or can address the system as a one-dimensional system. So these were our site selection criteria. We were fortunate enough to find a site that fit all these criteria, these stringent criteria, in Saskatchewan, Canada. Saskatchewan is identified as a little pink rectangle in the middle of the world. What I'll do is I'll blow up the southern third of that province. So the southern third of that pink rectangle looks like this. On the left-hand side is the province of Alberta. On the right-hand side is the province of Saskatchewan. This boundary here is the boundary between Canada and the United States. The site that fit all these site selection criteria is located 140 kilometers south of Saskatoon. We call it the King site. Now, to show you the laterally extensive nature of the geologic units in this area, and to identify the three units of interest to us, I will show you a cross-section across the study site. And it'll also cross a lake called Lake Diefenbaker, so you can orientate yourself, along the cross-section.